Okay, so first of all, thank you to organizers. I was not aware of this conference 10 days ago, but it's really nice conference. So thank you for putting this, especially now that we haven't much opportunity to have physical conferences. So this talk is a common work with Said Kasmi and Nathan Gillett. It's an example of new types of methodology to derive observational constraint, in which I will only focus on global mean temperature, and so we try to constrain projections and sensitivity of global mean temperature by calculating projections which are conditional on historical observations. So I will take a few slides to explain the method, and I'm happy to talk in this session because I see many relationships with what Peter Cadwell has shown before, and we'll try to explain this. Okay, so I start describing the method with an illustration. This is a collection of semi-fixed model response to a SSP2 4.5 scenario from 1850 to the end of the first 21st century. And so you see, so there are 22 semi-fixed models here with just a basic smoothing applied to highlight the forced response. And you see the spread, which increases with time. And so the first thing you can do to describe this distribution is to model it with a multivariate Gaussian distribution. And so if you fit such a distribution, you get this type of mean and confidence range. So I calculate the confidence range at each year, and you may try to put observations in this plot and look which of the simulated trajectories are consistent with the entire time series of observations. And you see that clearly over the most recent decades, a few responses simulated by models are obviously not consistent with observations, either because a few of them are too warm already over the recent period, and a few others are not warm enough. And so there is an attempt, in our case, to calculate the distribution of all these time series, including the future values, conditional onto these observations, which is what is shown here. So the pink range is the unconstrained semi-fixed range, and you get a constrained range after conditioning by these observations in red. Okay, so now if you put all this into equations, there is a summary in this slide. So the vector of interest is x. It's basically a time series of the forced response from 1850 to 2100. You get a time series of observations, y. And you first of all use the collection of semi-models to build the prior on x. And then you express the observations as a subset of x plus noise. And noise in observations comes both from internal variability, but also measurement uncertainty. So you have this covariance matrix for y, which accounts for the two effects. And so it's quite easy because everybody is Gaussian here to calculate the distribution of x given y. And that's what we do. And so the mathematics here are exactly the same as you do in Kriging and also in Kalman filtering. So it's basically the type of questions we had with Peter. That's exactly the same thing, but just the Kalman filtering here is only a one-step filtering. There is no iteration. So in my view, it's a bit closer to Kriging, but it's still the same idea. So now I go to the results. Of course, the first thing we want to do is evaluate whether this type of constraint works, and we do that using a perfect model evaluation. So we basically pick one model and try to predict the future ramming of that model using pseudo observations over the historical period from that model, so up to 2019. in that case. And so the target is the late 21st century warming in a high emission scenario. And so this plot shows again in peak. So you have a collection of models, and in fact run because there are individual runs. So a few models like CNRS have a large number of runs. There are 25 runs from the same model. The black point in each case represents the warming effectively measured in or simulated by this model. The pink red range, sorry, is the prior, and the red range is what is predicted by the constraint as a method using pseudo observations up to 2019. So the interest of this evaluation is to measure the coverage probability, and because we compute 90% confidence range, we expect to find a 90%, well, the true value lying in the computed confidence intervals in 90% of the cases. And what we can calculate in this example is very close to 90%, because if we depending how you count, but if you give one vote to each model, we basically find a 91% coverage probability, which is a good guarantee that the method is not overconfident. And also another attractive result is that there are a few models with a bit outlier in terms of the expected warming, like CNRS, but also other models which are simulating very low warming at the end of the century. And the method still seems to be able to predict also these kind of outliers, meaning that yeah, it does a correct job. So then you can apply this technique to the real data. And so this is illustrated here for the three main scenarios in CMIP6, so SSP 2.6, sorry, 4.5 and 8.5. What I think is interesting with this technique is that you use the entire observed record, so there is no arbitrary choice of a specific period of time over which we could calculate a trend or something like this. You take the entire time series, so there is, yeah, kind of exhaustivity in the use of available information. You can constrain the past, the near term, and the long term change. So you have something which is not dependent on a given target period. In terms of results, what is surprising, maybe compared to other similar studies, is that the constraint affects both the upper end and the lower end of the unconstrained model ranges. Primarily, this technique revises the expected warming downwards, but also the smallest value for the future warming are also excluded. And finally, we find that the uncertainty ranges in the late 21st century are reduced by 50%, which is relatively large in my view. A few other results. It's quite easy to extend this technique with a larger vector X to other metrics such as TCR or ECS. So I give here the numbers for these values. And one thing, so this plot on the left shows a collection of results for various scenarios again and time period over the 21st century, but I wanted to stress on metrics of sensitivity here. And I will not comment differences with CMIP5. So the orange bars show the difference. So the result, if the same technique is applied to a CMIP5 ensemble, but I will not comment these differences. What I would like to comment is the fact that, okay, as I said before, primarily the constraint by historical observations revises model range downward. So we exclude the models with the highest sensitivity. But at the same time, if we compare our constrained ranges, so the plot here, the red range are only the constrained ranges. If we compare these constrained ranges to the previously published AR5 likely ranges for a collection of scenarios, or even for sensitivity, either TCR or ECS, in fact, we primarily exclude the lower end of these AR5 ranges, which is kind of paradoxical. So I will not comment this graph, just to mention that this technique can also be used to implement attribution, again, by extending the vector X. And so it's a nice way to get a consistent view constrained diagnosis of climate change, both in past and the future, including contribution from individual forcings. And by the way, it could also be used to estimate the total warming to date. And what we found, if we applied it to the year 2020 exactly, is a warming of already 1.22 degrees, which is higher than previous estimates. Okay, so I get a few key messages here on key result, in particular the fact that the spread in late 21st century is pretty much reduced, and also the fact that the lower end of AR5 likely range is excluded. But I would like to stress on one limitation of this technique, which has been discussed again in this session, and is the fact that the sampling of model uncertainty is still very limited, because we are using 22 CMIP6 models. It's not a lot, and I think this would benefit from using large PPEs. Probably multimodal PPEs would be the best way to try to sample uncertainty a bit more comprehensively, at least better than ensemble of opportunity. Okay, and so this work is should be available soon now, because it's technically accepted by Science Advances. Thank you.